Glad to see that it's working. Yes, it's working fine. Perfect. Glad to see that it's working. Okay, so we are ready in 2 minutes. Just, I don't know if you have water or if you have any questions, yes.
Water, I forgot my water. Yes, yeah. Good point.
Yeah, because you are starting the first, so you better get ready.
Okay.
And just a quick check, actually, Miguel from University of Strathclyde, is that how is it pronounced? Strathclyde?
Strathclyde, yeah.
Strathclyde.
Yes.
Moises
Yes,
from the University of Lisbon and Rafael Luque, University of Córdoba, right? Okay.
Correct.
Miguel's connection, I don't know if, yes, you were blocked for a minute.
I think, yes, I think I'm back. It was just a glitch probably, yeah. Sorry.
That something happens, like just for a minute. Okay.
Miguel, if you have some problems at some stage, perhaps it would be good for you to turn off your camera.
Yes, that's
no,
no, I will do it. Yeah, sure.
Yeah, because in this way you save data and
bandwidth. Yeah,
data will be flowing better. And
okay, I will start the webinar. That is 10, so we will start broadcasting.
Okay, perfect.
Hello everyone and welcome to the latest MDPI webinar on materials that is entitled Advanced Porous Materials. Thank you very much for joining us today. This is the second webinar of a series that is based in special issues and sections of our materials journal. So if you are interested to submit your paper in the special issue related to this webinar, please check the webinar's website. Our chair today is Professor Rafael Luque from University of Córdoba in Spain, and we'll have 3 speaker presentations. Dr. Miguel Jorge from the University of Strathclyde in the UK, Professor Moises Lutzia Pinto from the University of Lisbon in Portugal, and our chair, Professor Dr. Rafael Luque. At the end of the session, we will have a Q&A session in which we will address all of the questions submitted by live online audience. So please, if you're joining us live, type your questions in the Q&A box that is at the bottom of your screen and mention the name to whom you address your question. I would like to remind everyone that this webinar is being recorded and that the recording will be posted soon in the webinar's webpage. Now I'd like to introduce our chair. Dr. Rafael Luque is professor in the Organic Chemistry Department at Córdoba University in Spain. He has been leading a research group since 2009 and has over 600 publications and several patents, as well as numerous prizes and awards. Professor Luque is also director of the Center for Molecular Design at Synthesis of Innovative Compounds for Medicine at RUDN University in Moscow, Russia, being also distinguished chair professor from the Department of Applied Chemistry at Xianyao University in China, and more recently, distinguished scientist at King Saud University in Saudi Arabia. He has expertise in multidisciplinary areas related to sustainable chemistry, nanotechnology, and materials science and engineering. He is also editor-in-chief of the Porous Materials section of our Materials Journal. So now I hand over the floor to our chair, Rafael Luque, and please, all of you, enjoy the webinar.
Thank you very much, Elena, and a very good morning to everybody. Thank you for joining us, and I hope you will enjoy our presentations today that will be covering different topics from more theoretical and computational aspects of materials design and engineering. That will be our first speaker, Miguel Jorge from University of Strathclyde. And then moving on to adsorption, separation, and chromatography for our expert Moises Pinto from the Technical University of Lisbon. And then moving on to the third topic that we will cover today related to materials chemistry, that is catalysis. And that would be me delivering the last presentation of the session. That will be followed by the Q&A session. As Elena has already mentioned, please type your questions in the Q&A part of the Zoom for us. And we will try to address all of them and make sure that you include all of them before the end of our presentation so that we can start with the Q&A session right after our presentations. So without any further ado, let me introduce the first speaker of today's session, or a fully Iberian session today. Miguel Jorge, it's a chemical engineer, in fact, that received his degree at the University of Porto, followed by a PhD already at the UK at the University of Edinburgh in 2003. He has been holding several positions as full-time researcher at the UMass in the US and the University of Porto before reallocating again to the UK when he moved to the University of Strathclyde in 2013. And then he became very recently senior lecturer at the end of last year. Miguel's research that you will see in his presentation in a little while applies molecular modeling techniques, including Monte Carlo molecular dynamics, to understand systems that range from molecular simulation to a wide range of industrial approaches and to understanding, chemical engineering and applications in adsorption, in material synthesis and characterization, in thermodynamics and phase equilibrium, so very complex systems, including the physics of interfaces and of course, nanotechnology. He has published over 80 scientific publications in international scientific journals and delivered many invited seminars and conference presentations, including this one of today. Miguel is currently also director of the postgraduate research in chemical engineering at Strathclyde and is regional editor for the journal Molecular Simulation. So Miguel, the floor is yours now, so you can share your presentation and we will be delighted to hear what you have to tell us about this very exciting molecular dynamics applied to materials synthesis. Thank you.
Thank you very much, Rafael and Elena, for the kind introduction. I will share my screen so you can see the slides. So yes, I mean, the talk is about modeling. That's the first thing to understand. My work has been on modeling materials, several aspects. We also do some work on adsorption, prediction, and other things related to materials. But this talk in particular is going to be focused on modeling porous material synthesis, in particular, porous silica. So it's a subset of the work that we do, but it's where we've made quite a lot of advances quite recently. So the first thing to understand in terms of the modeling is the issue of length scales. And so if we start at the top, we have conventional chemical engineering simulators like process simulators, etc. Also computational fluid dynamics. All of these modeling techniques make use of a continuum approximation of matter. So, everything is continuous. You have a fluid, you have materials interacting at a continuum level. But of course, if you're interested in processes that go down this scale into the micrometers and millimeters and nanometers, then you have to start to take into account the discrete nature of matter. And these mesoscopic methods here, like lattice Boltzmann and DPD, take that into account. And many of these methods are actually hybrids. So they, for example, take up discrete elements like particles or cells within a continuum, flowing within a continuum medium. If you go further down, that's where my training lies, right? In molecular simulation at the nanometer scale, where the fundamental unit of matter is the atom. Okay, so we describe systems as collections of atoms that are bonded together and interacting with each other. And then further down this scale, you go into the quantum level where you actually start to treat protons and electrons, subatomic particles, as your discrete entities. Okay. What I'm going to show in this talk actually bridges all of these length scales in the discrete side of modeling, right? So down from the quantum level through molecular atomistic modeling all the way to mesoscopic methods, because if we want to understand material synthesis, we actually have to bridge all these length scales. So just a very brief background on molecular simulation. Essentially what we do is we replicate or we simulate a lot of microscopic states with molecules interacting with each other. And these are characterized by positions and velocities and momentum of each molecule. And then using laws of statistical mechanics, those laws tell us how macroscopic properties, macroscopic thermodynamic properties, emerge from the interactions at the micro level, okay? So essentially we connect the microscopic level, which we simulate, to macroscopic properties that we can compare with experiment, okay? And so in many cases, you can see a molecular simulation almost like a virtual experiment, a computer experiment, because once we specify the model for how the particles interact with each other, then we have a way of predicting these macroscopic properties. So as I told you at the start, one of my areas of work is in computational material design. So we try to develop computational methods that can predict how a material is going to be formed and then how it's going to perform in real life applications. So to do that, we must address two essential vectors, which is how do we connect the synthesis conditions, pH, temperature, concentrations, etc., to the structure and properties of the material that is synthesized at the end. This link here is what this particular talk is about. But a second link is also important because it's when you know the structure and the properties of the material, how can you predict how it performs? For example, in gas separation, in sensors, in catalysis, etc. Now we do some work, as I told you, on adsorption related performance, but I'm not going to talk about that. And in fact, Moises is going to talk a lot about that in his talk later. So this talk is going to be about the first link here. Okay. And of course, the aim of my group's research is to use models to help inform this understanding and help guide experiments in synthesizing and discovering new and better materials. So as I told you, this involves bridging several length scales. Okay. So we start from quantum level. We do some quantum calculations on molecules, on small molecules, to obtain essentially parameters like charges and geometries of molecules that allow us to then develop these classical atomistic models, which are classical in the physical sense, right? So there are no electrons or protons here, but all the atoms are represented explicitly and they can interact with each other through intermolecular potentials. But then, as I'll show you, this is not enough for us to understand material synthesis because material length scale is much larger than 1 or 2 nanometers. And so then we have to go all the way to these mesoscale level models, which now start to treat atoms or interaction sites as collections of atoms. Okay, I'll show you how that's done in practice. But the key step here is that we need to actually make sure that we retain all the necessary physics when we go up a level in length scale. Because of course you're simplifying the description of the system because you're making the calculations much faster. But you pay a price, of course, you can't keep all the physics. So you need to make sure that you calibrate the models accordingly so that you can keep the essential physics that determine the outcome of the simulation in a way that you can actually make these large-scale models be quite realistic, okay? And this approach, actually, this is a very crucial point, this last point here. This allows us to maintain the chemical specificity, because if you start at the high level, then you can understand things, but you don't really have a counterpoint or a direct relationship with experiment. And our models do, and I'll show you that. So I'm going to talk to you about three cases or three examples of materials that we deal with. And the first is the very typical example of mesoporous silica. Many of you will know this, this class of materials. The typical example is MCM41. Okay, and this is a electron micrograph picture of MCM41. And you can see that actually it's composed of walls of silicon dioxide interlinked with each other. And the pores are organized, are relatively cylindrical, and they're organized in these hexagonal arrays, which are really quite nicely ordered. But typically there's no order in the pore walls. So the pore walls are disordered. Okay? And these are well-known materials since the early 90s. You know, we use for many things like gas separation, catalysis, sensors, drug delivery, etc. Okay, protein encapsulation, several things. What's the key aspect of the synthesis? In order to get these pores ordered in this particular way, you have to use a template. And a template is something that keeps the shape of the pores while the material condenses, the scaffold of the material condenses around it. And so this is the diagram here. You have surfactants organizing in micelles, which are cylindrical. And that's this gray area in the middle. And then you have silica condensing, polymerizing around the surfactants to form the shell of the material. And at the end, you burn off the surfactant, you leave the holes, okay? In a nutshell, that's how it works. Now, what's the problem with this? The problem is no one really understands how these hexagonal arrays are formed completely, because experimentally it's very difficult to probe all the steps of the reaction, okay? And that's what we're trying to do in our models. We need to span a wide range of time and length scales, and we're doing that with multi-scale models. Okay, so as I told you, we started from quantum calculations. We started this work in a very good collaboration with my colleague José Gomes in University of Aveiro in Portugal. In fact, when I was still working in Portugal, this was back in 2008. And so we started off by doing quantum calculations on silicates to develop a new model for silicate species in solution. And then we use that information to build this new atomistic model. Okay, so we have the surfactants here, which, as any surfactant, has a polar head here, which is positively charged in this case, and a hydrophobic tail here in green, which tends to aggregate and form these micelles. Okay, and then the medium is aqueous solution with some counter ions, and then we have the silicates present in the solution. And because the synthesis of MCM41 is typically done at high pH, all of these silicates, or nearly all of these silicates, have a negative charge, okay? And as you'll see, they will interact quite closely with the surfactant head, which is positive, okay? I'll show you that later. So before we proceed to the next level, we stretched the atomistic simulations as far as we could. And so we were able to see that silica, when you add silica to a solution, which is formed of these surfactant micelles shown here on the right, then it starts to interact with the heads of the surfactants, and it forms this silica shell around the surfactant micelle. And this plot here shows density profiles as a function of the distance to the micelle center. So you start at the middle, you have only tails here, and then you start to see this purple head group layer separating the micelle surface from the water, which is in blue. Okay, and then the counter ions are here in black. When you replace the silica by the bromide counter ions by silica, you see a big shift. It starts to adsorb a lot closer to the surfactant heads, and it increases the micelle size. Okay, this was the first main insight into the mechanism. But of course, the problem is you can't go any further because the simulations are very expensive, so you can't simulate larger aggregates. Therefore, we go through the next step, which is now to coarse grain the model. This coarse graining means that we aggregate groups of atoms together in beads, which are much larger. And this therefore makes the simulation much faster. But again, you pay a price, you make the model simpler. So you need to make sure that you get the correct physics. Your surfactant still behaves in the same way as the atomistic one, and your silica still behaves in the same way as the atomistic one. Just as an aside, for those of you who are more technically minded, we use the Martini framework to develop this coarse grain model. So you can look it up in this reference here at the bottom. Okay, so this is the first step of validation, right? So we need to make sure, as I said, that the coarse grain model here at the bottom, works the same way as the atomistic for what matters, which is the micelle formation. Okay, and you can see that the density profiles agree really nicely. We calibrated the coarse grain parameters to make sure that this was the case, and we formed the same type of micelles. Okay. We can also see that the surfactant, so we validated against the atomistic models, the higher level of theory, but we can also validate against experiment. And this is a phase diagram of the pure surfactant in water. And we've ran simulations across the whole range of concentrations, and you can see that we form the correct aggregate morphology. So at low concentrations, you form spherical micelles, which is the starting point for the material synthesis. But as you increase concentration, you form rods. There's a sphere to rod transition. Then you form these hexagonal liquid crystals of surfactant, and then you form these lamellar phases. Now, the key to understand here is that the material synthesis, the MCM41 synthesis, starts from these micelles here with silica, not here, okay, not at the high concentration. So we need to understand what actually happens. So this is a starting point on the left, aggregate of, or an assembly of micelles, spherical micelles of surfactant. What happens when you add silica monomers? This is before any silica is allowed to react, just adding silica to the system. And all of a sudden, there's a profound transition, okay? The silicates interact, as I showed you in the previous simulations, interact closely with the surfactant and essentially changes the balance of charge at the surface of the micelle, and enables these micelles to merge together and elongate to form these long rod-like shapes. Okay, and this is seen experimentally. So that's the first step. But still, what we saw was that when silica was in monomer condition, you didn't see anything else except these rods. So no aggregation, no hexagonal structure. So then we tried something else. Again, validation against experiment. We started from this experimental benchmark study from Brad Schmelke's group in Stanford, in California, who actually did some very rigorous experimental characterization of the synthesis solutions. So we knew exactly what the concentrations were, what the pH was, what the speciation was. It was dominated by these cubic silica octamers. And so what we did was we simulated exactly this system. And this is what we got. Okay? We got the formation of these hexagonal liquid crystal arrangements straight from the bat, from the simulation, just replicating experimental data. Okay? So this matches the hexagonal liquid crystal formation. And this is the first model that was able to do this under realistic experimental conditions. So we were happy with this achievement. We published that in Chemistry of Materials in 2016. But then we did a bit more. We tried to understand the physics of why this happens. Okay, why does the silica enable this formation of hexagons? So I showed you this. We start from random configurations of surfactants leading to micelles. And if you add silica monomers, you form these worm-like rods. But if you add dimers, so instead of monomers, the silicas now are able to react and form a dimer, then already you form hexagonal liquid crystals, okay? So for some reason, you need the silica reaction to start happening, the polymerization to start happening, to change again the balance of interactions in the system. And what we also showed was that all these are equilibrium systems, because if you replace monomers with dimers and vice versa, you can translate between these two structures. So essentially, the key element is that once you form a silica dimer, you have a molecule with two negative charges that acts as a bridge between micelles. So one end is interacting with one micelle, the other end is interacting with another micelle, and so that enables the formation of these bridge structures, which then promote the formation of these hexagonal liquid crystals. Okay, so this is really interesting insight we got from this simulation. And this is an atomistic, so we can do back mapping, and we can look at what actually this looks at the atomistic level. And we can see that this is exactly what's happening. These silicates are now interacting with two different micelles and bridging them together. And so the whole process is driven by these charge matching interactions, so balancing the charge at the surface of these micelles. So then we can play around with the model and see how we can control the mesostructure. So we can go from changing the degree of polymerization of the silicates. So going from here, we have 4 dimers to 2 tetramers, and then all the way to 1 octamer. And you can see that you can change the morphology from cylinders all the way to lamellar phases. Okay, this is quite interesting. You can also achieve the same idea by changing the charge of the silicates, which essentially is related to the pH of the medium. Okay, so as you increase the pH, again, you go from these cylinders to these lamellar structures. Okay, so again, it's all about the charge at the surface, right? You can control that by the extent of reaction, of polymerization reaction, but also by the pH controlling the deprotonation equilibrium of the system. You can also play around with co-solvents, and this is again to try to replicate what has been done experimentally. So if you put in something like benzene, for example, then you swell the inside of the micelles, the hydrophobic region, you increase the volume of that region, and that again shifts the curvature of these aggregates and forms these lamellar structures. And then you can remove the benzene and revert back to the hexagonal. Okay, so again, these are reversible equilibrium transitions. And this is, again, mirrored what experimentalists see in their And then just to conclude this part of the talk, we actually spanned the whole phase diagram of this class of materials, and we were able to see under which conditions, by increasing surfactant concentration, we can form MCM41, but also this cubic bicontinuous MCM48 structure. And finally, at very high surfactant concentrations, you go back to this MCM50, which is a lamellar arrangement of pores. Okay? So this kind of concluded our analysis of this class of materials. And so we decided to move on to other different types of material. So one of them was the second type of material that I'm going to talk about is mesoporous organosilica. Okay, so the arrangement is the same. You still have these hexagonal structures, but now the pore walls are changing, right? And how this works is the following. So instead of having just silicates, which would be this top end here, you have a hybrid organosilica precursor, which means that you have two silica moieties here connected by, an organic group. Okay, in this case, we're using benzene, and I'll show you why in a second, but you can use any other thing, ethylene, naphthalene, etc. So people have played around experimentally with a lot of these precursors to get some really interesting materials, which kind of combine the best of silica materials, mesoporous silica, but also with the functionality of organics, because then you can start to play around and functionalize these benzene rings, for example, with amine groups or something like that for carbon capture, etc. Okay. So these benzene silica materials are quite interesting because apart from forming this order at the pore level, they also, the benzene rings stack together to form these ordered pore walls, which are really quite interesting. So we did, as I explained, we started off by doing quantum calculations on these precursors, then atomistic MD simulations. And these were done in 2013. And you can see already what happens is that you start to see the preliminary steps of this aggregation and alignment of benzene rings, okay, to form these stackings that lead to the pore wall ordering ultimately, okay? So that's the first evidence. And then we went on to develop very recently another coarse grain model, but now for these organosilica materials. So now we have the silica beads as before, but now we've developed two beads for the organic ring, which have this kind of diamond-like structure to mimic the organosilica precursor. And then we started playing around with this. These are very, very recent results, which we published last year. And we showed that actually adding these organosilica precursors to the initial micelle configuration allows us immediately to form these hexagonal liquid crystals. Okay? And the difference is that now we have, whereas before we had monomers of silica, and that was only an equivalent of this red bead, now we have the two monomers bonded together by this organic group. And that's already sufficient to act as bridging linkers between these micelles. And so we saw already that this can promote the formation of these hexagonal mesophases. So no polymerization is needed before this mesoscale structure is formed, and that allows perhaps a greater degree of control over the pore structure of the material. Okay. Now we're expanding these studies now to look at other kinds of precursor and liaising with experimental colleagues to try to develop ways to improve the synthesis of these materials. So I'll move on to the third class of material that we've looked at, which is bio-inspired silica. Okay. Now, these are really quite interesting materials, I think, from my point of view, because they're inspired by nature. So the idea is to take insight and information from the process of biosilicification. So we have all these organisms in nature, diatoms and sponges, etc., that can actually capture silica from aqueous solution at room temperature, at low concentration, just from the sea, for example, okay, seawater. Then deposit them in these hierarchical, beautiful, porous structures, okay? And, you know, people have been studying these for years, and there's still no understanding, no complete understanding of the mechanism for this biosilicification. But what is known is that there's a key role played by polyamines and amine-containing peptides. So amine groups seem to be quite key for the development of this hierarchical structure. Okay, so why is this interesting? Also, it's interesting fundamentally, but also it's interesting, you know, from a practical technological point of view, because the problem with the materials, the MCM type materials that I showed you before, is that those are synthesized typically at very harsh conditions, high pH, or you can do it also at a very low acidic pH. High temperature, you require also calcination at the end to remove the surfactant, you know, toxic chemicals, etc. So it would be absolutely great if we can now learn from nature and develop synthesis methods that can be done at neutral pH, low temperature, with low concentration solutions and no toxic chemicals. And that's precisely what one of my colleagues at Sheffield, Siddharth Patwardhan, is trying to do, is trying to develop bio-inspired silica materials. So we're collaborating with them to try to understand this mechanism a bit better. We started off, one of my PhD students a few years ago started off by looking at the earliest example of these bio-inspired silicas templated by amine surfactants. So key difference from the materials that I showed you before. The previous materials had ammonium surfactants, which means that the charge on the head group is permanent. So it's always positive, right? You cannot protonate or deprotonate the surfactant. With amine groups, on the other hand, you can, right? So we can change the charge level here at the head of the surfactant by changing the pH, okay? So at very high pH, these groups are neutral, but as you lower the pH beyond about 10 or 9, these groups start to become protonated and charged. Okay, and we looked at two prototype systems from the work of Tanev and Pinavai in the late 90s. So one is this HMS material, which has the same structure as the MCM41. Patterns are different, and the nature of the interactions at the surface is different. So these guys postulated that everything takes place with neutral species, neutral silica and neutral surfactants. Okay, we'll see exactly how that works, or whether that actually works like they postulated experiment. We also looked at these other class of materials forming vesicles, but I won't have time to talk about these, but there's work on these materials as well. So again, we developed these atomistic and then coarse grain models, the key now being that the surfactant needs to be pH responsive. So we have models for the protonated and deprotonated amine groups. Okay? The difference is the head group, which is charged in this case, and neutral in that case. And our experiment to show that the pH is not neutral in the synthesis of these materials. It's about 9. And at that pH, actually about 85% of the amines are protonated, and about a quarter of the silicates are anionic. So already from basic experiments, we can already see that the postulate of Tanev and Pinavai's neutral templating mechanism is probably not correct, because there's a lot of charge going around the system. Okay? And so what we try to do is then run simulations to understand what's happening really in these systems. So these first set of simulations are for the charge system, okay? So we see that as we add the silica to the system, you start from a micelle structure, you start to form these rods, and then you form this aggregate, which I'll show you a bit better in this picture, but has a more disordered hexagonal array of pores. And then, crucially, what we did was we replicated a hypothetical neutral system as postulated by Tarev and Pinavaya, and actually we saw that nothing happened. We just form a blob of surfactants, and the silica is not interacting with the surfactants at all. Okay? So, in a nutshell, this neutral templating mechanism, which has been accepted by the scientific community for decades, is actually not viable. It's not happening in practice. And so we then put together this diagram to put together the information on PMS materials like MCM41 at very high pH, where you have everything driven by charge interactions. And this lower pH synthesis of amine templated HMS materials, which because of the lesser degree of charge lead to more disordered arrays of surfactants, but nevertheless, the charge interactions are what lead to the formation of these hexagonal liquid crystals. Okay, and we published that in Materials Horizons a couple of years ago. So just to conclude, hopefully you've seen that we can do interesting things with multi-scale modeling to understand how materials are synthesized and try to develop predictive techniques to aid experiments in discovering new materials. So everything that I've shown you points towards a cooperative templating mechanism where it's not only the template itself that is responsible for the onset of the structure of the pores, but actually the interaction between the template and the silica groups. Okay, that's what's driving the order in this cooperative way. And really, as far as we can see so far for these systems, everything is driven by charge matching. Okay. So we need silica oligomers, or at least bridges, like in mesoporous organosilicates, to form these mesophases. And we can control the degree of order of the mesophases. Okay. So just pointing out a few challenges, right? So we're trying to now develop techniques to improve the order of these bio-inspired materials. We have a PhD starting just now with that. And also we're trying to explicitly model the silica condensation reactions at the same time as self-assembly. Again, in collaboration with our colleagues in Aveiro, we're trying to develop this. So I'll just finish by thanking all my collaborators in the MCM41 synthesis simulations, the bio-inspired work, and the organosilica synthesis here. And I thank you all for your attention.
Thank you very much, Miguel, for your excellent presentation, and particularly for keeping up the timing so well. Congratulations. And we will leave the questions for the Q&A session, remember, but we have already a couple of questions already on the way, so things will get exciting at the end. And without any further ado, I want to introduce the next speaker of our session, Moises Lucia Pinto from IST Lisbon. So Moises obtained his PhD in chemistry in 2005, same as myself, at the University of Lisbon, with studies on the development of composite adsorbents for gas-solid adsorption. So he's an expert in adsorption. And after this, he went for a postdoctoral research stay at the CISECO at the University of Aveiro, also in Portugal. He was research assistant for a couple of years at CISECO. And then he got assistant professorship position at the chemical engineering department of IST, where he currently is. He published over 80 publications and is a regular referee in scientific journals, coordinating several national and European research projects at the Centro de Recursos Naturais e Ambiente, and he's vice president of this research center currently. His expertise is mostly on adsorption. And Moises, the floor is yours now. We will love to hear about the adsorption properties of some porous materials. Thank you.
Thank you, Rafael. Thank you for your kind introduction. So I will start by sharing my screen. Okay. Just a few seconds. Okay, thank you very much. So I will try to show you here a little bit on the on what we have been developing and studying recently, related with gas adsorption and separation with hybrid porous materials. Some of these, as you will see, are very closely related with the ones that also Miguel has just highlighted now. But in this case, well, we already have been hearing about this, so periodic mesoporous organosilicas. This is one type of hybrid materials where we have these organic moieties that are bridged in between silica type bonds. And the other one is mesoporous silicas that can be functionalized with organic moieties also at the surface. So we can, how to say, synthesize first the mesoporous silicas, and Miguel has highlighted a very interesting approach to understand all the details about these very complex systems from the point of view of the synthesis also. But afterwards, we can introduce we can decorate the surface of these pores with organosilicas moieties, and we can then tune the surface of the materials. Another type of materials that is now very well in the last 2 decades has been rising in terms of the developments of types of materials and applications are the metal organic frameworks. So in this case, what we have, as you can see in here, are these organic bridges in between some metal clusters. In this case, these are zinc tetraedra that are interconnected with these naphthalene rings. Well, this is a MOF, IR MOF 8, and we can obtain these three-dimensional arrays like this, in this case, cubic type pores. And we have, of course, this porosity, as you can see in here for this particular case, but the structures can be much more complicated, much more intricated. As you see in here, we have also, in this case, some organic linkers. This is the same organic linker, but in this case, it is being assembled in this way to produce, in this case, with chromium tetraedra, producing a very, well, a MOF with a big pores. This is the case of MIL 101. But as you can see in here, we can use the same linker with the different type of inorganic nodes. In this case, with zirconia, and as you see in here, we obtain a completely different structure with these tetraedra and octaedral pores in here. So just to give you some idea, we can even play like, okay, assuming that we have a piece of a Lego and we can, how to say, compare this with the structures that we are building, we can even increase the size of this linker, and we can obtain bigger pores just by increasing the size. Of course, that from the synthesis point of view, sometimes we will have problems because we cannot increase this indefinitely. We will have problems of interpenetration and so on. But actually, the main message is that with this approach, we can obtain hybrid materials with very tailored properties. And I hope that at the end, I can be, how to say, I've convinced you that indeed this approach to the synthesis of hybrid materials can be very interesting for gas adsorption and separation applications. So I will start just by talking a little bit about CO2 separations. And CO2 separations, we can look at it with two different perspectives. One of them is the one that I would say many people are now, and also the society, are looking for. So we need to reduce the emissions of CO2. So CO2 capture from stationary sources, it's one approach. But there is also other perspectives that are very important. For instance, for upgrading methane-rich gases, we need, in this case, to remove CO2 from natural gas or landfill gas, also biogas sources. So we need to do this to increase the heating power, also avoid corrosion problems, and we need also, instead of just removing components without commercial value, we can also remove other ones with more commercial value. These are rare on biogas, but they appear sometimes on natural gas. So in this case, we are talking not on carbon capture, but on methane upgrade. So from the perspective, from the application perspective, what we are talking about is, in one side, we have application for CO2 capture. So we have a fuel that is burning, we have the flue gas, and then we hopefully have some porous adsorbent that retains CO2, and afterwards we are emitting, already clean gas. The other perspective, it's different from the application point of view, but the concept is also very similar. So we have landfill or biogas, and then we also have an adsorption process. And then in this case, we are aiming to separate methane from CO2. But as you see, so porous adsorbent it's in the heart of the system. So regeneration of the adsorbents bed by lowering the pressure or increasing the temperature can be done. And this is very important from the process point of view, because it means that we can use or reuse in several cycles these materials. Of course, that the efficiency of these processes is highly dependent on the efficiency of the adsorbents. So it's very important to develop new materials and to test them, because we can, play a lot with the process and to increase the efficiency from the engineering of the process perspective. But we cannot, extend more than a certain efficiency, because this is related with the equilibrium and kinetics on the porous adsorbent. So I will here show some very briefly examples on how we can use periodic mesoporous organosilicates for the CO2 adsorption. So in one work, what we have done was to, in collaboration with colleagues from Aveiro and also with Miguel Jorge also, I collaborated with them in this approach of understanding how PMOs with different functional groups at the surface could be used to separate CO2. In another approach, conceptually different, was to use initially PMOs without any modification, so pristine PMOs, and after the deposition of aluminum oxide at the surface with atomic layer deposition, we can also obtain these composites, and this can also change the properties. Another approach is to pick up the pristine PMOs and make a treatment at high temperature, so some pyrolyzing them, and to obtain some materials that are different from the previous ones. So we when we change these materials, the surface, we can see in here, so we have here the plots of selectivity. So selectivity can be regarded and should be regarded as a, a preferential adsorption of, in this case, CO2 over methane. So in fact, this number gives us how much more CO2 is adsorbed inside the material comparing with the composition on the gas phase. In fact, give us the separation that we can have for a process, the maximum one. So in this case, as you can see in here, when we have normal phenylene PMO, we have selectivities around here. But when we have some amines at the surface, as we see in here, we can increase this selectivity significantly. From the process point of view, this is a very important improvement. when we do some atomic layer deposition, you see here also an increase depending on the number of cycles. In this case, when we have 15 cycles of deposition, the aluminum oxide that we have at the surface of the pores will increase the selectivity also significantly. So we have an increase from from here to here. And as you can see here, comparing with just a mixture of PMO and alumina, you see that in fact it's significantly different. Why? Because in atomic layer deposition we have very how to say small clusters of alumina at the surface of the pores, and of course this interacts much more strongly with the molecules that are absorbed in the pores. So this is much better than just mixing the two materials. In fact, as you see here, this comparison really highlights the benefit of the deposition with ALD. So depolarization, as you've seen here, I will not comment on all the results we have, but as you can see in here, we have a significant increase in this case when we have this polarization at high temperatures. So the main message that I want to give to you in here, so in this case, we can see that primary amines are in fact the most efficient ones. In this case, another approach is to make the deposition of alumina that also interacts strongly with CO2. And also in this case, the thermal treatment also improves the efficiency, particularly for this PMO that is more stable when we put it at high temperatures. We have also developed significant work in amine functionalized mesoporous silicates. These have been used for CO2 adsorption. Functionalized amine silicates have been used very much in the last decades. But what we wanted to understand is really what is going on at molecular level. So we use several techniques, including some NMR advanced techniques and computational DFT methods. And essentially, what we wanted to see was the stability of the species, the energetics of the process, also the chemical nature and the possible structure. I will not go into all the details, but I will try to highlight the main topics, the main points that we have seen in here. So, just to put again into context, we started with this type of mesoporous silica. So in this case is SBA15. It's a mesoporous silica, as you see in here in this nice electron micrographs, and you see that the pore size it's about 7 nanometers, and this material can be decorated with these amines, so these organic tails in here with the amine. So we have primary, secondary, tertiary amines, and also a mixed amine, so secondary and primary amines. Well, as you can see in here, we have a significant change in the adsorption property. So we have here the adsorbed amount as function of pressure. So this is what we call adsorption isotones, in this case up to 10 bar. And you can see in here, when we go from the SBA 15, the pristine one, to the functionalized ones, especially with the primary, secondary, and tertiary amines, as you see in here, we have a significant increase in here, particularly at the low pressure, because at high pressure, it's lower than SBA 15 because we are also occupying the volume of the pore. So this is a balance between changing the chemistry of the surface, but also keeping still a significant volume for CO2 to be absorbed. And when you compare with methane, you see that methane, in this case for biogas upgrading or methane upgrading, you see in here it's completely different. The adsorption in this case, methane is not interacting strongly. So what we have actually done was to try to understand what was the species that were being formed, yes, and also to understand what is the effect of pressure. So we seen here that we have this formation of at least these three moieties. We have used labeled CO2 to increase the signal in NMR. So we seeing here the increase of the signal with the pressure that we put in the system. But very interestingly, not all the species are being formed at the same time. So well, and we can see also here the free CO2. Okay, in this case, can only be seen in this site, because in here it needs to be how to say, close to the species that are being formed. Okay, so our identification was, in fact, as we will see, is that this peak is related with the species forms, in this case carbamic acid or carbamates, when we have both of hydrogens sorry, both of the oxygens in here making hydrogen bonds, in this case just one making one hydrogen bond, and in this last one when we just have this type of interaction of one side. So but to get to this conclusion, we have also tried to understood what was the influence of water. As you seen here, if we put just a little bit of water in the system, we are decreasing these peaks, and this is because water is going to make hydrogen bonds with the species that are formed at the surface. So we are removing the possibility of these two. And also we can see in here that we can in fact go back and remove the chemically bond species by making vacuum. So people have been telling that it's difficult to remove the chemisorb species. In this case, this is not happening. We can remove them with vacuum, as you can see in here. So if we compare the signal of the propyl chain that we see in here and comparing with CO2 already bonded, so the chemisorb species, initially we have this relation in here. So but when we start to make high vacuum, you see that it decreases and becomes in the same order of magnitude, just with 5 minutes of vacuum. Well, we have afterwards done a careful study for correlating the CO2 signals of the carbon and proton in the systems to understand what are the relationship and the acidity also of the protons that are involved. And in this case for the primary amine and for the secondary amines, and we have seen here differences in the acidity of these protons. And also one other very important information is the correlation between the proton signal and silicon signal. As you can see in here, we can understand also that some so some silanol groups at the surface are also interacting with the same protons that we have seen over there previously, interacting with the carbamic acid and carbamate groups. So it means that we have a very, how to say, intricate network of hydrogen bonds. So summarizing what we have concluded also using some DFT models is that we have, well, these type of structures that we see in here, so for primary amines and for secondary amines, and we can compare these signals with the ones before, and we have concluded that in fact when we have 154, it means that we only have hydrogen bonding here at this position. When we have hydrogen bonding at the top position, we have a signal at 160, so it's doing this type of interactions with the lateral amines that we see in here. So we can see in here also another situation when we have secondary amines. Well, just coming back a little bit. So as you seen here in this case, just to highlight also, so you seen here that we have some silanol also playing in the system. Yes, so this is very important. So and lastly, the one that is more intense, 164 ppm. As you can see here, we have concluded that we have an interaction with a lateral amine like this, and an interaction also very strong one with the silanol at the surface. So in terms, going back into for the adsorption and selectivity, in terms of adsorption and selectivity, we can see in here a very high increase of several orders of magnitude, because it really steeps at very low pressures. And this can be related with the formation of the species with pressure. So we can correlate, how to say, the increase of the amount with the species that are being formed at the surface. Okay, these ones are formed at very low pressures first, and then we move on for the other ones after. Okay. So another topic that I'm going to talk about briefly, it's about ethane and ethylene separation, using, in this case, metal organic frameworks. And we started our studies on this topic with adsorption in IRMOF 8. So in this case, as you can see in here, what we want to have, it's a different type of adsorption from the classic materials. Classic materials tend to absorb more ethylene than ethane. In our case, were looking for materials that absorb more ethane than ethylene. And these are not very common ones. Now more and more people are looking into MOFs for this. Now we have more examples, but when we started with IRMOF 8, only one case was reported in the literature. As you can see in here, in fact, ethane absorbs more than ethylene, and we see here the selectivity. And we try to understand why this was the case, and we also use some DFT modeling. In this case, we try to understand how the molecules would interact with in this case, the small clusters like this that represent a part of the IRMOF. So we have the linker in here and the two metal nodes, and we have the electrostatic surface potential mapped in here. And we can see that some of these positions, as we can see, for instance, in this case, in fact, corresponds to a slightly stronger interaction for ethane than ethylene. So this is the case, this is one of the cases, and in here also one of the cases. What happens is that later on, when we try to model the ethane and ethylene adsorption using GCMC, so to obtain the isotones, we have understood that in fact the model that we were thinking on initially were not giving the proper description, as you see here. So this is the experimental points, and these in here are the calculated ones. Even changing the how to say, using different potentials to run the simulation doesn't change this. So the problem was a conceptual. So the structure cannot really describes the experimental data. So what we have done afterwards was to move to try to understand and look in the literature, and we have found that in fact people were reporting some interpenetrated structures for IRMOF 8. And in fact, when we use this interpenetrated structure, it means that we have two intergrown structures of IRMOF 8, and one is growing in the middle of the other one. So the space is it's more crowded, as you can see in here. So in the end, when we use this structure to run the simulations, we can see a proper description of the system Yes, and you can see in here also when we compare the experimental well, the selectivity calculated from the experimental points with the selectivity estimated from GCMC simulations, it agrees very nicely. Also, the phase diagrams agree very nicely. So the experimental points with the line in here, it's very interesting to see that in fact when we changed the how to say the structure, when we run with different structure, we are able to describe this. So our conclusion is that in fact IRMOF8 with interpenetrated structure is the one that is giving the good selectivity for this separation. A second work that we have done was to compare, in this case, zirconium MOFs, so with different types of cages. So in this case, tetrahedral and octahedral cages, and in this case, in here with just channels. As you see, we in this case play with a linker, like I've just said before. We have a naphthalene in this side, so we have bigger pores, and in here we have just one benzene ring. So going to the results, you see in here also the simulation points and also the points and the lines that are the experimental ones. So we afterwards can from here calculate the selectivity, and in fact we see that in this case the structures with three-dimensional pores are more interesting to this separation, are giving the ethane selectivity. So this we can see in here. So we have also here, so YO66, the typical MOF. And in fact, our understanding is that when the molecules are in three-dimensional pores, they can interact with more linkers. In this case, we have, as you can see in here, we have the linkers are not fully aligned in these chains. So it means that one molecule can only, adsorbed molecule can interact only with one of the linkers inside. So in this case, this is not so effective. We also explore the substitutions on the linker. I'm just showing here for CF3 groups. And as you can see in here, using these perfluor groups at the surface, we increase also the selectivity. This is very interesting. What happens after is that it was more difficult to explain the adsorption, because in this case we need to include in the part of the simulation the possibility of the linker to be rotated, because this is a very, as you can see in here, a very crowded structure. So we introduce this type of rotation and re-optimize the theoretical with theoretical approach with the periodic DFT to obtain new structures that correspond to also to minima. And using these, so I'll try to show very briefly in here. So if we don't have any rotation on the linker, we have adsorption just at the tetrahedral pores. But if we have some and no adsorption at the octahedra pores, but if we have some rotation of the linker, then we don't have adsorption at the tetrahedral cage, but we have adsorption at the octahedral ones. And we have some, how to say, in-between situations that correspond also to minima on the structure. So if you see in here, the difference in the energy of the structure is not very much, but nevertheless, it changes quite a lot the porosity and the maximum pore diameter. And in fact, it also changes the adsorption in terms of ethane and ethylene. So what we, our interpretation is that when we start to adsorb ethane and ethylene, we have some small rotation in the pores. And in this case, ethane seems to open more the octahedral cages, so it can adsorb more at the structure, and explains the results, these very interesting results. So just to wrap up my talk and the main messages to keep. Well, I think I've shown here some examples that hybrid materials can be tailored to produce porous materials with new chemical environments, and we can use these chemical environments to play with the interactions with adsorbed molecules, and we can tune these structures with different types of pores. So the pore geometry also plays a role, as we have seen, but also to use functional groups to be able to have more interaction with preferential interaction with just one type of molecule, and this selective interaction can give can be used to have effective separation of gases. In fact, gas separation by adsorption with hybrid materials can be an effective alternative for industrial applications for these challenging separations, especially the ones that are not easily addressed by classical adsorbents. Well, just to give you also, well, to thank you for your attention, and also to acknowledge the collaboration of all colleagues that have been working on these topics with me in the last years. Thank you very much.
Thank you very much, Moises, for your presentation. We have a few questions from the audience, so we will go through them after the next presentation. But now we move on, and fortunately I don't have to introduce myself, so this will be rather quick. And we will move on to the last presentation of this symposium that will be delivered by me on catalysis, on porous materials for catalysis. So I hope you can see my presentation, which in fact, at the beginning, I was planning to prepare a very short introduction on catalysis and industrial processes, of course, the catalysts of the future and the materials of the future, in which we are increasingly able to design some catalytically active materials that can provide comparative advantages over industrial and as well as long time experienced materials in terms of activity, selectivity, and particularly stability. I will make a special emphasis on this, and taking into account, of course, the green chemistry principles. So you will see in my presentation that in fact, there will be several benign by design strategies. So we focus on waste reduction, we focus on atom economy, without losing the touch, without losing the topic of catalyst efficiency. That's also very important. We focused in the past few years in a research group on renewable feedstocks and on biomass and waste as a source of chemicals, materials, and fuels, focusing also on energy efficiency and, in essence, reduced toxicity that is achieved by the use of more sustainable solvents, even in less quantities, and alternative methodologies such as mechanochemistry, in which we are able also to engineer the catalysts of the future. And this is one example that you see that in fact relates to the research topics of our group. I will come back to this, that encompass activities in nanoscale chemistry, heterogeneous catalysis, biocatalysis, and photocatalysis, flow chemistry, that is in fact something that brings us one step closer to industry in terms of scaling up and in terms of providing the alternative methodologies and processes to benchmark industrial systems as compared to these that we have synthesized in terms of activity, but most importantly in terms of stability, and biomass and waste valorization. That has been a very relevant topic for the group in the past few years, that we have approached towards the design of new biorefinery concepts based on these biomass and waste valorization steps. So the presentation of today, in fact, is going to be based on three main topics and three main types of porous materials. Porous materials that we can engineer via advanced mechanochemistry processes. Most that I'm glad that Moises and Miguel, but particularly Moises, has extensively described and disclosed in his presentation. So we'll go directly to the topic itself and to the example itself. And then a couple of tailored benign by design porous nanostructures that show some relevant catalytic activities, and we can fine tune based on these benign by design strategies. The stability of porous materials, in fact, is a very relevant topic that deserves a special attention and help us to benchmark also the activity and especially stability of these systems towards industrial catalysts. And under continuous flow conditions, we have proved some successful cases and some not so successful cases. So today I bring one of each so that you can see the differences and in fact, how can this can help to design the catalyst of the future. Finishing with some conclusions and some future prospects. Okay, so the first example that I bring on mechaноchemically designed materials, in fact, brings me to the topic of mechanochemistry, which perhaps some of you are not so familiar with, but mechanochemistry is nothing different than introducing different energy into a reaction or into a synthesis as compared to heat or radiation electricity. So the mechanical forces that come into play that are in fact no different from the manual grinding that I'm sure that every single person in this room has done at least once in their careers when they were undergrads, can be more controllably tuned using designer instruments in which we can play with different parameters under these ball milling conditions in order to go from neat grinding to liquid assisted grinding and so on for nanomaterials design. In this particular case, we have found a lot of interesting features of this mechanochemical approach, which in fact, as you see, after more than 10 years of research in the topic and of research related to mechanochemistry, this turned out to be a very useful technique, a very useful tool to design advanced, highly active and stable nanomaterials that can be in fact synthesized under very mild conditions generally. So we're talking about a few RPMs and short times of reaction, very swift and very simple preparation that in our simplified systems, of course, we can go to more complex systems, takes about 5 to 10 minutes. But also a protocol that allows an incredible tunability. So it allows a lot of flexibility in terms of fine-tuning the catalyst pre and post-synthetically. And in fact, the post-synthetic treatment is the one that I'm going to disclose today in my presentation, dealing with highly active nanomaterials that can be achieved even at very low loadings, that have highly accessible sites, particularly for bulky molecules, because they are preferentially located on the external surface of the material, because it is essentially a surface technique. So these frictions and this mechanochemical step per se, and in some cases with the possibility to fine tune the nanoparticle size in the system. Not so easy for those that are already starting to ponder and are going to make the question, not so easy for shapes and for other types of more sophisticated materials. For this, another bottom-up or even top-down approach is more relevant as compared to mechanochemistry. But in the example that I bring today, in fact, the incorporation of aluminum was conducted on mesoporous materials, on SBA15 type of materials, and the mechanochemical conditions post-synthesis. And in fact, it turned out to be a successful framework incorporation, even if at very low quantities that you see in the slide, 0.2 to 0.5 weight% of aluminum was incorporated. But this aluminum incorporation, as you will see, particularly that we could obtain from a MOF precursor, from aluminum containing MOF precursor after decomposition, allowed us to conduct very selectively and nicely active, very simple, but otherwise important selective oxidation reactions. So in here you have the example of the different materials that was synthesized in this work. For comparative reasons, of course, a conventional hexagonal mesoporous material, SBA15, was synthesized. A comparative SBA15 with aluminum incorporated conventionally using a conventional impregnation deposition protocol was prepared as compared to the mechanochemical incorporation. And this M stands for the mechanochemical incorporation, in which two different aluminum precursors were selected. Same as the one for impregnation, aluminum isopropoxide for this particular ALM, and a MOF and an aluminum containing MOF as aluminum precursor that was synthesized, the material was synthesized after mechanochemical incorporation. So the idea was to obtain and to achieve aluminum dispersed and isolated sites on this SBA type of 15 material. Fortunately, there were framework aluminum species, as we will see in a little bit in their NMR spectra. And these turn out to be the most active from all materials that we will see in the series. So the incorporation, in fact, within the framework was confirmed, as it can be seen in here. You can see that there was a framework incorporation as compared to the extra framework aluminum that, of course, and obviously is present in every single post-synthetically synthesized material. But we found that some significant quantities of aluminum framework species within the actual structure were incorporated with our mechanochemical treatments. The aluminum content was, of course, too low to be seen, of course, but we can see the profiles of the aluminum of the SBA15 type of materials. We have indeed some additional evidences by infrared. And the most remarkable thing, in fact, relates to the most interesting thing relates to the actual reaction itself that can be catalyzed under these conditions. So we selected a very simple chemistry that you see in the slide. In fact, this is the selective oxidation of sulfides to sulfoxides, avoiding over-oxidation to the sulfone. And in fact, the most relevant thing of this type of chemistries is that these were optimized previously in our group and was recently also published by the use of a heteropolyacid type of material, in which the loading of heteropolyacid was 40 weight%. So the heteropolyacid, of course, provided quantitative conversion and complete selectivity. So 100%, 100%. Conversion, 100% selectivity to the sulfoxide, which is this species. As compared to this optimal lab system, I draw your attention to the fact that these materials that we synthesized under mechanochemical conditions contain 0.2 to 0.4 weight% of aluminum. And with these premises, of course, the activity that you see is pretty remarkable, reaching close to 40% for the optimum type of material, with selectivities that are close to 60 to 70%, which is also pretty good. On top of this, I draw your attention to the reaction conditions that were selected for this particular chemistry, which, regardless of the amounts of sulfide, of the equivalence of hydrogen peroxide, and the mechanochemical reaction that was performed also on the mechanochemistry, I draw your attention to the catalyst loading. So not only 0.2 and 0.4 were selected, materials were selected for this particular reaction, but also a 0.04 molar percent was added as catalyst in the system. So this turns out to be 3 to 4 milligrams of catalyst that contains a 0.2 to 0.4 weight percent of aluminum, which, as you can imagine, stresses the fact that these catalysts were highly active and highly selective under these conditions and very, very low loadings. And again, shows the beautiness of this particular mechanochemical synthesis in order to achieve advanced, highly active and stable materials. Of course, for the stability, for those that are already wondering, ICP MS, of course, for traces of metals, both from the ball mill and both from the material, aluminum and other metals, including iron, for example, from the balls, was carefully conducted and they found to be non-existent. So the instrument sensitivity goes to 0.5 ppms and nothing was detected. So it is definitely below of this and not in any quantities that obviously will be able to catalyze a 40% conversion with 70% selectivity to this particular reaction. Again, showing the beautiness of this particular product. If we move to MOFs, I'm happy that Moises have already introduced these beautifully designed materials that we can engineer using linkers, organic linkers and different metals. So we have done extensive collaboration with South China University of Technology in this topic to engineer via self-assembly metal nanoparticles embedded within the MOF type of materials, core shell type of nanoparticles, clusters, and so on. And perhaps the most remarkable feature of these materials in terms of porosity and in terms of catalytic activities came up less than 3 years ago in Science, in which we reported the design of different porous single crystal MOF materials derived from ZIF8 that you see in there, that were synthesized using a very simple template type of approach using polystyrene beads. So following a simple impregnation, crystallization, and soaking in THF to remove the polystyrene bead template, we were able to achieve an unprecedented MOF type of material that feature a unique microporosity, of course, coming from the MOF, from the ZIF8, as well as the macroporosity, the very large pores that you see in these beautiful images. So featuring this macroporosity and microporosity, together with a single crystallinity that was reported for the first time in this type of MOF materials, we found out that these were nicely active, catalytically speaking. And our model reaction, which is in fact a very simple Nova-Nagel type of chemistry at room temperature, showed, however, that this extraordinary contribution of macro and micro porosity together with the single crystallinity was found to achieve excellent yields in this particular reaction that was selected as a model reaction as compared to conventionally synthesized MOFs that you see at the bottom on these Bs and the conventional hydrothermal conditions. Again, stressing the potential of developing this unique porosity in the materials as well as the single crystallinity. A follow-up paper of this is currently submitted on a biomass-derived application of the materials. Last but not least, these tailored benign by design nanostructures that you have seen, these beautiful catalysts that I mentioned at the beginning on these pig hairs, for example, for cleaning of effluents from different pollutants, from phenols, from dyes, and from so on, and the use of porous scrap catalytic converters as efficient nanocatalysts, because as you see in there, still after the removal of the precious metals that are contained with these scrap catalytic converters, we can have some traces of some precious metals, including platinum, in some cases palladium, in some cases rhodium. So these three vial catalysts that we have employed as active catalysts for simple chemistries again. This is a tandem type of reaction that you see was performed under continuous flow conditions, and it's cyclization, hydrogenation tandem chemistries for the preparation of menthols. So these are the structures that you see here, the menthols. And in fact, these menthols have been synthesized in very high yields from citronella, in this particular case, from citronella, via cyclization to isopulegol, and then reduction, hydrogenation of this double bond, exo double bond of isopulegol to menthols. So this is the first example of the continuous flow process that I was mentioning earlier on. So as you see in there, the activity of the catalyst was stable, was very stable after several hours, after 24 hours on the stream, under continuous flow conditions. And even the catalyst could be recycled for a second cycle, for a third cycle that I have not included for simplification of the figure. So this is a very stable system in which the stability of the metals, in fact, that are contained in the particular system was also considered and was also ascertained by ICP-MS, in which, again, it was shown that there was no metal leaching under these conditions. Remember that these materials contain only traces of platinum as main precious metal that was the one providing the hydrogenation activity for the double bond hydrogenation to a single bond for the production of menthols. So this was a highly stable system. And as compared to this highly stable system, we have another very interesting story to tell, which is the story of the stability of MOFs, which as materials are absolutely great, as I have shown earlier on in our science paper, but lack of stability under certain conditions. In this particular reaction, which is the methyl levulinate conversion to gamma-valerolactone, a biomass-derived platform chemical to a precursor of biofuels, we found a very peculiar long-term stability profile for these materials that turned out to be a not so successful case, because as you see, materials slowly deactivate with time, but we found out that the material is fully degraded after a few hours with time on stream. So for this particular example, we were very interested to push the stability of this UEO66, it's a MOF containing zirconium as metal, for this particular reaction under extreme conditions that you see in there. Of course, to push and to see how far we could get to test the stability of these MOF materials. So 240 degrees C and 35 bar of pressure are too extreme, and you will see why. But the interesting thing is that, and the take-home message, most importantly, is that if you decide to run the reaction under continuous flow conditions and stop after a few hours, stop here, stop after, I don't know, 5-6 hours, you will perhaps see that more or less the conversion is leveled off, you know, so it's this productivity, or even the conversion, which is this one down below, the conversion is pretty much leveled off. And if you stop a little bit earlier, you will see that, yeah, it's 85%, close to 90%. So the conversion is leveled off, and I bring here this one closer, see? Even increasing slightly, so you stop in here or in here or in here. But if you leave it for a longer reaction time, you find out that the material deactivates. So if you stop at this, you will say the materials are highly stable, but My recommendation, of course, and take-home message is to at least run a long-term stability run of 24 hours to definitely confirm that the material is nicely active and stable, such as in the example below, okay, that you're seeing here. 24 hours plus and a second cycle. While after this 24-hour reaction, because we saw that the catalyst was slightly deactivating, we ran a complete characterization of the system in order to check what was the cause of the activation. And what we found out, in fact, in this particular example, as you see in there, is that after 24 hours, there is no moth anymore. So there is no structure of the moth. And you see the material has degraded to be a very poorly porous material that, in fact, in this particular case, after further characterization by XRD, was found to be an amorphous zirconia phase. So from the original zirconium moth system, this zirconium atoms and these oxygen atoms were slowly released, and what was left in the end was a zirconia phase. So the moth structure was lost, and the zirconia phase, in fact, was nicely active, as you see. Was nicely active because even after 24 hours could retain almost 80% of the activity of the original system, but it is not the moth phase, the active phase anymore, but an amorphous zirconia phase that was left after the decomposition of the moth at the extreme temperature conditions that were employed for this system. So this is the take-home message. First, and most importantly, it's essential to run a 24-hour run under continuous flow conditions to fully prove that the system is highly stable. And the second, and not less important, to analyze and to fully characterize the system after reaction in order to find out whether the active phase that was originally present in the material is still present in the final catalyst. So with this, I hope I was able to convince you of the different possibilities that we have to engineer advanced porous materials using different methodologies, using mechanochemistry, going all the way to MOFs that we can also synthesize via mechanochemistry, but in some other cases, we can find out some other alternative processes and methodologies in order to fine-tune the porosity in the systems that has a significant influence in the catalytic activity. And last but not least, some of these nicely active porous catalysts, tailor-designed or tailor-made from waste, from biomass, that have been shown to be, in some cases, highly stable, in some other cases, not so stable under continuous flow conditions, but in any case, that we can engineer and we can characterize and make sure that the active species are responsible for the catalytic activity all the way throughout the process itself. With this, of course, many thanks to all my collaborators, co-workers, and colleagues, the different funding bodies that allowed us to do this very enjoyable research with the team and with the young people in my group. And of course, to all of you for your kind attention and for joining us here today. So we will start the Q&A session in a second. In case you don't have any time for questions, you have here my Twitter account. So make sure that you drop me some messages on Twitter, and then we can take it from there from some additional discussion on the topic. Thank you very much. Thank you. And now we will start with the Q&A session. So I will stop sharing my screen so that we can allow Moises and Miguel to answer these questions. And the first set of questions will go to Miguel because he was the first speaker. Mr. Shira, I hope I pronounced it correctly, wants to ask a general question How can we understand the concept of amorphous nature in nanoporous materials? And can we say that a material is amorphous if it has hierarchical pore size distribution? Please kindly explain what are the other physical parameters which determine the amorphous nature of a nanoporous material. Miguel, over to you.
Thank you, Rafael. So I typed already some answers to these questions in the chat, but I'm more than happy to elaborate on this. So the first is, it's a nomenclature issue in a way, right? I mean, normally a crystalline material is determined by the nature of the fingerprint of the X-ray diffraction experiment. So if you have several peaks of Bragg order, essentially, you have a molecular periodicity in the material, and so it is determined to be crystalline. At the other end is an amorphous material which shows no evidence of order whatsoever. Now, these materials that I talked about, the MCM41 and the derivatives of MCM41, as well as, for example, mesoporous carbons and stuff like that, they are really quite interesting because they're somewhere in the middle between amorphous and crystalline. Yeah. And so, some people call them semi-ordered, hybrid ordered, I like to call them mesoscale ordered, right? And the reason is because most of these materials are disordered at the atomistic scale. So the pore walls, the organization of the atoms is kind of random, but they have order at the pore level scale, okay? So in the XRD experiments, they show a big broad peak at long length scales, right, corresponding to long length scales, but no order at the atomistic scale. Now, I'm not a purist, right? You call it whatever you want, but essentially it's something in between, right? It's neither here nor there, neither completely crystalline, neither completely amorphous. It's something in between. The mesoporous silica, incidentally, just to conclude this point, the periodic mesoporous organosilica materials, some of them actually show some order peaks at the atomistic scale because of that stacking of the benzene rings and formation of this order at the pore walls. Now, there is debate on whether those are really crystalline materials like MOFs and zeolites, or whether they're still somewhat amorphous, but I'm not going to go into that.
Okay, thank you, Miguel. So we had a couple of, well, not a couple of, but 4 questions from Awais, but you have answered them. So he has 2 or 3 for Moises. So we will move on now to Moises. Moises, so Mr. Chirac again is asking on how efficient that phosphorus-rich nanoporous materials in densifying and absorbing CO2 as compared to nitrogen-rich materials.
This is a broad question. I would say that it also depends on how do you have the nitrogen and the phosphorus at the pore surface. I mean, for instance, if you have nitrogen-rich materials, but if the nitrogen it's not able, for instance, in this case of the amines, for instance, if you have tertiary amines, they are not so effective to bond CO2. Okay, you have amines at the surface, but you don't have protons that can, exchange with the CO2 to form carbamic acid or carbamate. So, and this is the same thing as for phosphorus-rich materials. If you are considering to have some type of chemical bonding between the CO2 that arrives at the surface and the species that are over there, it also needs to be taken into account how these chemical species are, not just if they are phosphorus-based or nitrogen-based. Yes, so you can have. Saying this, it means that you can have phosphorus-based materials at the surface that are more interesting than some nitrogen-rich materials, because it really depends on how they are at the pore surface. Yes, and this is not, by all means, this is not an easy task, because sometimes, for instance, with the mines, you try to put the mines at the surface, but then with time they can tend to oxidize or degrade and so on, so you lose some efficiency. In the case of putting some inorganic species, more stable ones at the surface, for instance, like alumina or this type of, it's better from the point of view of stability, but also they are not so effective initially, it means. So it's not an easy answer. You can have materials, phosphorus-rich materials better than mine, nitrogen-rich materials, or the other way, depending on how is the chemical, the chemical nature of these species at the surface. Yes.
Thank you very much, Moises. On another question from my dearest Fateme Rajavi, she wants to know if you have examined the pure alumina for CO2 captures compared to the aluminum PMO that you were showing.
Yes, in fact, over there we have shown, pure alumina, if it's not a porous alumina, it will not absorb significantly. You just have, well, non-porous alumina will not be. But considering a porous alumina, this can be an option, and in fact, this is already used at the industry. But the question is, the pore volume of these alumina usually is not so big as those of PMOs. Over there, the idea was, how to say, to combine the chemical affinity of the alumina. So you have some ILOH groups at the surface of these particles that we depose over there that are very acidic and then can interact very strongly with CO2. But at the same time, we have a very open framework, mesoporous of PMO. So this is a way of, how to say, trying to combine, I think in the materials field nowadays, this is a trend. It's trying to combine things that we already know that are working from classical materials with other new materials and try to combine them at molecular scale, let's call it this way. And so coming back to the question, alumina, porous alumina, they perform well at, in terms of selectivity, but in terms of capacity, they do not perform so well. And for application at large scale, both of these things are very important, because I didn't talk too much about these engineering aspects, but if you have a material that is very selective, but the capacity is very low, it means that you will need a huge volume of the material to be used in a certain process, and this is not attractive at all. So a lot of things need to be taken into account, also the stability and so on, before being applied. Yes.
Perfect. Thank you, Moises. Awais has a couple of questions for you too. So the first one, in fact, relates to different MOF materials, If8, UEO, with excellent properties for supercapacitors, even in some cases for adsorption. So he's asking what will be happening if we use this type of systems for photocatalytic CO2 conversion, because we have a national source of sun, of course. If it will be cost effective with these coordination compounds, which I guess the question is, well, very relevant because these are expensive type of materials.
Yeah.
And if they will be, or if they would potentially have some applications for industrial premises, CO2 capturing.
Well, of course, I mean, the framework of the question, I think it's, okay, we have CO2, but if we capture it, we need to do something with it. And in fact, photocatalysis could be a way of transforming CO2 to something else. I think this is what is in the background of the question. And in fact, there are a significant number of papers in the literature reporting MOFs that can catalyze reactions with CO2 and photocatalytic reactions. Okay, if you go with and I would say that with zirconium-based MOFs and titanium-based MOFs, yes, these I think are the ones that are performing better. Nevertheless, this is a question: zirconium and titanium-based MOFs are, from the conceptual point of view, at least with these metals, are not the cheapest ones. If you choose iron or aluminum MOFs, in principle, it depends, of course, on the linker in the process of the synthesis and so on. But at least from the point of view of the precursor, they are more cheap, yes, than zirconia or aluminum MOF, or titanium MOF. But as it happens also in many other fields of catalysis, is sometimes you have some catalysts with very expensive metals and so on, and they are used in industry. If they perform very well, they can, how to say, they can pay off. It means you can assume this is always a question of performance versus price. So I mean, if you go for several catalysts that are used in industry using noble metals, they are used nevertheless. They have very small amounts to do the catalysis. Oh, well, you know better than me, Rafael.
Yes.
And they are used. So,
yes,
I mean,
absolutely.
I would say, yes, they can be used for sure, as long as they pay off the price of being more expensive to prepare. Yes.
Yeah. My comment also related to this will be that in fact they can be useful, and the stability of the systems and the quantity of metal that is needed in order to achieve a comparative performance is absolutely essential in order to reduce the overall cost of the whole process, because the catalyst itself for this type of industrial processes, it's going for 50% of the process, really, of the price, of the cost of the process. So
Yeah.
I fully agree with you. This will be, in fact, in some cases, I hope the catalyst of the future, but of course, extensive optimization and consideration of these important aspects needs to be taken into account for industrial premises. Thank you, Moises.
Okay.
Another question for you. In a catalytic conversion of CO2, from Mr. Chirac again, is it mandatory to have CO-philic moieties, azo groups, OH groups, to absorb CO2, even if the material itself is capable of chemically activating CO2 and capturing, for example, FLPs?
I would say, yeah, from what if I really understood the question is do we need to put these groups if the material itself is capable? I mean, if you want to have a reaction of CO2 at the surface, as you have seen over there with the mines and so on, you really need to have some groups that can activate CO2. CO2, it's a stable molecule. It's we can call it this way. So not going too much detail, but if you look at a thermodynamic diagram, so CO2 usually stays at the bottom comparing to almost everything. So this is a question of going from this, how to say, wealth on the stability. So we need to have very specific and strongly bonding groups if we want to react CO2 afterwards. So I think if it absorbs CO2, but in, how to say, just physical adsorption, I mean, for catalytic applications may not be sufficient. I mean, we are increasing the concentration at the surface, okay, but I would say that it is not sufficient. So usually if you look into the people that are using CO2 activation at the surface, you always need something that bounds CO2, okay, effectively, let's call it this way, not just physical adsorption. It's impossible.
Can I add maybe something there, Moises? Actually, you know, you guys know better than me, but also from the catalytic point of view, you want to have the CO2 residing for long enough at a specific position, whereas with adsorption is migrating all over the surface.
Yes.
Have localized.
Yes.
Adsorption.
Yes.
That's right. The point. That's the point.
You need to have a species that is, how to say, an intermediate, more unstable than CO2, and need to stay over there for sufficient time. As you have seen in the results I have shown for mines, there are many people using also mines for catalysis of CO2. And you see over there, we can measure the peaks in the NMR, so they are stable, they stay over there. So it's this is why it works also from the point of view of catalysis. Yes, this type of species that are formed at the surface.
Great, thank you both. Okay, so we come back to Weiss again. So I'm going to combine these questions 2 and 3. So he's, of course, it's well known that other metals, including ruthenium, silver, can be incorporated into MOFs and even graphene oxide for composites. So what do you think, Moises, or also Miguel, that are the prospects for such materials, such hybrid materials with MOFs in terms of applications for CO2 adsorption? And if we can capture, can we capture 100% of CO2 emissions using carbon capture and storage technologies?
Well, I think from the point of view of application of these metals, I would say this is similar to a little bit with our previous discussion. I mean, you can use these metals. They are already being used in classical, let's call it catalysts, as long as the performance clearly justifies the cost. These are, well, silver not, but ruthenium is very expensive metal. Silver a little bit less, of course. I think yes, and probably Rafael, you can comment much better than me on this. These new structures can give you the possibility to have, how to say, very isolated atoms of these, let's call it almost isolated ones. So they are more active, and you spend less metal to cover up the surface. From this point of view, I would say, in principle, this is a good perspective for using these metals and these materials. This is a plus. So going for the 100% question of the carbon capture emission, this is a tough question. I mean, people, of course, now we have a framework also across the globe, not just in Europe, of pushing forward for carbon capture. But I would say that if you look at the emissions levels right now, I would say that it is impossible just to rely on carbon capture. This is not possible at all. So the people that I've been talking with that are much more specialists in the energy, how to say, market, and also related with CO2, they all of them highlight this. So it needs also to be, how to say, complemented with a change on the energy source. So we need to change from, let's call it, carbon-based energy. Well, eventually, if we have some biofuels and so on that are renewable, they are not contributing on the overall, but at least from hydrocarbons, we need to reduce significantly the use of hydrocarbons and coal-based energy. And so I think we cannot only rely 100% on carbon capture. It's impossible. Okay, it's impossible.
Yes, I agree with you, Moises. And for the first part, single atom type of systems are the future. So for this, I have just copied in the chat for all our attendees a recent preprint from our group that is also published in Green Chemistry and Environment journal from the Chinese Society. And in this particular one, we have evaluated the potential for single atom catalyst as an industrially viable technology. So it's a long discussion, but in any case, this is where the future is heading right now, and we will see more and more developments in this particular regard. Okay, so Arvind, he has one question on amorphous materials. So he's preparing amorphous materials, and he wants to go for NMR, solid state NMR, I understand. Mm-hmm. But unfortunately, he doesn't get any peaks in NMR spectra. So this is more related to research. Mm-hmm. Being an amorphous material, it's not possible to go for X-ray crystallography. Can you please suggest how can I characterize this type of material? So Moises, Miguel?
I'm not an NMR expert, but I've been using it for a long time. Maybe I can give some, how to say, clues. Okay, from what I understand, the question is not obtaining just a single NMR peak. Sometimes what you have, for instance, if you look at the spectra that I've just shown for protons, for instance, usually they are very broad in materials. So because, well, just how to say, explaining very simply, it's because these are changing quite a lot. The dynamics of the system is very fast, and the moieties, the number of moieties, for instance, in silica-based material is almost infinite. So what you see are some trends over there, some big, how to say, not sharp peaks, but
Very broad peaks,
yeah, very broad ones.
Very broad peaks, yeah.
So I'm assuming that you are commenting on this. So usually what is good is to try to do these advanced techniques that I've shown over there. For instance, if you have some silica-based materials and we have proton also over there, let's try to correlate how the silicon signal correlates with proton. And then try to correlate, for instance, over there, we try to correlate how carbon signals are correlating with protons. Why with protons and not directly with silicon? It's because on the experiment, we need to transfer energy from the proton to other, how to say, nuclei. And protons, as you know, so the abundance of proton is almost 100%, but carbon 13 or silicon 29, it's much less. So we usually rely on this transfer of proton of the signal to the other ones. So is what we call CP. So in this case, you can try to have some clues on what is the vicinity of these nuclei, and can start to give you some clues on how to say general trends. If the material is amorphous, this is not going to be like, for instance, a crystalline morph where you just have one peak just correlating with another one. Usually you have a broad band that is correlating eventually with one peak of silicon and eventually with one peak of carbon. And if you want to use NMR, my advice is try to talk with someone that, how to say, can program the machine and has quite a lot of knowledge in the field. I'm not an expert, I already said it, to try to do this type of experiments. Yes, and usually it pays off. At least you can try to understand what are the, how to say, typical vicinities of the nuclei. Let's call it this way.
Yeah, thank you, Moises. So I have
Can I just add, Rafael, very quickly?
Yes, yes, please, Miguel.
Maybe the insight can also begin from other more indirect techniques. I mean, you can do some spectroscopy trying to find the chemistry of the links inside your material, but also even nitrogen adsorption, right? If you're looking at the pore structure is organized, right? I mean, looking at calculating a pore size distribution from nitrogen adsorption is quite insightful normally for amorphous material.
Yeah, perfect.
Yeah, helps you get an understanding of what's actually in there.
Great suggestion, Miguel. Thank you.
Yeah, thank you.
Okay, so the last question, Anand, is actually two questions. How do you see mechanochemistry in a long run in terms of scalability? Okay, so we'll firstly address this. This is something that I normally address, in fact, in some of my presentations, because in fact, mechanochemistry has been scaled up already. So there are several ball mills that are adapted to different types of mechanochemical type of approaches. We have extruders, you know, like the large scale extruders. We have scale ball mills, and in fact, in a collaboration that, for example, we do have some interesting collaborations with other groups, including the group of Professor Giancarlo Cravotto in Italy. He has access to intermediate scale up for a lab ball mill in which you can synthesize kilos of materials. So this is already a reality. And of course, it will become a more future reality related to the advanced design of these materials. In terms of my views on the synthesis of drugs, using heterogeneous catalysis, using flow chemistry, well, Anand, what can I say? This is what we are doing now. I have 2 proposals, 2 projects now, one European project related to this on greener pharmaceuticals. So particularly on greener halogenations of some APIs. And this is essentially the future. So 50% of the project that in fact is one of these Horizon 2020 proposals, it's on flow chemistry. So we take care of the flow chemistry part of the scaling up, and the aim, or one of the deliverables of the project, in fact, is the synthesis of one of the products, one particular halogenated product with a fluorinated moiety on a 20-liter scale by continuous flow chemistry. So there you go. This is definitely the future. And in terms of scaling up, it's a more viable technology as compared to mechanochemistry, because it's already on the way to scaling up. Many pharmaceutical companies are already heading into flow chemistry and even into photoredox reactions, photoredox chemistry, so in flow, which is a hot topic nowadays. I hope this answers your questions. Arvind is the last one. Okay, Anand, thank you very much to you for attending the symposium. Arvind is saying that the pore size distribution is down, so I guess he doesn't have pore size distribution. I don't know if you have any other alternatives for this, but I would agree completely with the comments from Moises. And even the XRD will give you some broad bands, but with the correlation, you can get more or less information on what you have. Yeah. Okay, so if there are no further questions, no further comments, let me thank again Moises and Miguel for their excellent presentations, for their insightful comments and the nice discussion we've enjoyed for a few minutes, which in fact is being over half an hour. And let me thank also NDPI for the possibility to give us this chance to deliver our presentations and to organize this webinar that I have seen, in some cases reaching more than 100 participants that have been very successful. I have nothing else to say from my side, unless Elena, that is at the background and wants to say something.
Yes, just a quick thank you to you as well, Rafael, for chairing this session, and Moises and Miguel for your presentations. We hope to see you all in upcoming events, material events, and take care, stay safe. I will then close the webinar now. Bye-bye.
My pleasure. Take care.
Goodbye.
Thanks for everything.
Thank you all.